We've already talked a little bit about this idea of how we can get more accurate approximations or even an exact approximation using Riemann sums, but I just want to demonstrate it to make sure that everybody's kind of visualizing the same thing. So what I have here is a curve, just kind of a generic curve. If I wanted to use one, here I'm using a left Riemann sum, so this is a left endpoint rectangle, okay? So if I wanted to use one rectangle to approximate the area under this curve from, sorry, from from A to B. This is the rectangle that we would get, and its area is 10.2. The actual area is 8.814. This is kind of what we're trying to get close to, so just keep an eye on that number. If I increase the number of rectangles, we've already kind of talked about how as we increase the number of rectangles, we're going to get more precise or more accurate areas as our approximation. As you can see, we can go pretty high with this. And actually, let's go, go by tens. Okay, so the more and more and more rectangles I have, I think it goes up to 80, the closer I get. Now, even with 80 rectangles, that's still not exact, but it is definitely closer than just using one. All right, let's get rid of this. Let's go back to 1. Okay, and then if we do a right rectangle, obviously we have quite a bit of over approximation. And again, the more rectangles we have, the closer we get, and we could average those. Obviously, we don't want to do this by hand. Okay, let's see, let's hide those. Midpoint, again, same thing. We go up pretty high, and then I just want to show trapezoidal approximation just to kind of see. Yeah, I mean, right off the bat, even with the trapezoidal approximation, we're very close. Now, it says the exact same thing, but I suspect that's because of just a rounding thing. It's not going to be exact unless we use an infinite number of figures, trapezoids, rectangles, whatever they are. And so we're going to look at how to represent that next. Okay, so the actual area that is under the curve, and by the way, we are only talking about positive curves right now, so we can use the word area. If part of the curve is negative, we're going to run into, in a little bit, into what happens or how we handle that. But when we're talking about the area under a curve that's positive, it is going to be the sum of the areas of an infinite number of rectangles. Okay, we want that number of rectangles to approach infinity. So let's figure out how to express all of this analytically so that we can evaluate it without obviously having to come up with the areas for an infinite number of rectangles. All right, so I've got this curve, just a generic curve, positive curve here, f of x, and I have an interval from a to b, and we're going to be cutting this into an infinite number of infinitely thin little rectangles. Now, obviously, what I'm drawing is not infinitely thin, but we can see that we, just to visualize, that's what we're doing is each of those rectangles is shrinking to a width that approaches 0. Okay, so if I have a generic rectangle in here, I'm going to call this my ith rectangle, okay? Then, actually, let me not label it right there. I'll label it up here. So this is going to be the ith rectangle. So I've got the first rectangle, second rectangle, third rectangle, all the way to ith rectangle, etc. Okay. I want to figure out how to write things in terms of that general rectangle, because then if I can find the area of that general rectangle, then I can add all of those areas together, and that's going to get me my area, my overall area. Okay, so my number of rectangles I'm going to call n. And then the height of each, actually, let's skip to width. The width of each of the rectangles is going to be the total length of this interval from a to b, so that distance is b minus a, divided by the number of rectangles n. So the width of each rectangle, which I'm going to call delta x, is equal to b minus a over n. You may see this written as delta xi sometimes, which is fine because it's the width of the ith rectangle, but all of the rectangles will have the same width, so it doesn't really matter if we put that I there or not. Okay, and then the height of each rectangle comes from the output of the function at a specific point that is on the subinterval. And we could use a left endpoint, we can use a right endpoint, we could use somewhere in the middle, but really it doesn't matter if all of the rectangles are getting infinitely thin. So if this is my starting point, x sub 0, then one rectangle over would be x sub 1, two rectangles over would be x sub 2, etc. So this point right here is going to be x sub I. And the height of the rectangle, the ith rectangle, is the output of the function at that point, f of x sub I. Okay, now we are going to figure out how to express that in terms of the function. Well, our starting point is at A, which is the left endpoint. Okay, so the first rectangle would, if we use the let's say we're using left endpoints here. Again, it doesn't matter in actuality, they're going to be the same. So that means that the first point, x sub 0, is the same as A. For the second x coordinate, so moving over one rectangle, that would be x sub 1. That's the same thing as saying the starting point of the interval plus we've shifted over by delta x or delta xi one time. Okay, the second x coordinate, you may see what's happening here, is the left endpoint plus, now we've shifted over by two rectangles, so 2 times delta xi, okay, etc. And then the nth rectangle, the ith rectangle, not the nth rectangle, is going to be the starting point plus I times delta x. Okay, and again, or delta xi. And again, delta x is b minus a over n. All right, so the area of the ith rectangle is the height of the ith rectangle, which is f of x sub I, which is going to be f of this. I'll fill that in a minute. And I'm going to multiply that times the width of each rectangle, which is delta xi, okay, which is equal to, so now let's put all of this in terms of b and a and n, because a and b are n is the variable n, but a and b are going to be given to us in the problem. So it's going to be f of a plus I, whoops, that's not an I. I'm cheating here with my paper. Okay, it's I times delta x, which is b minus a all over n, okay? And then times delta x, which is another b minus a over n. Now, it does not matter if you remember it in terms of like x and delta x, or if you remember it in terms of a and b and n, or even if you remember in terms of delta x, you're going to have to put it in terms of a and b and n, which will make more sense when we do an example here. But it doesn't really matter how you remember it. The important thing is you need the width of each rectangle, which is the total length of the interval divided by n, and then the height of each rectangle, which is the value of the function at each of the inputs or each of the x coordinates for x, and that is x sub I, or a plus I times delta x. Okay, putting all of this together, I know that's a lot of letters, so stick with me. Putting all of this together, we are going to take an infinite number of rectangles and add all of their areas together. Okay, well, to add all the areas together, we're going to use a summation, which is why we reviewed sigma notation. And then to make an infinite number of rectangles, we need to start with a limit. So that area is equal to the limit as n approaches infinity, so n, remember, is number of rectangles, of the sum from 1 to n is the total number of rectangles again, of f of xi times delta xi, or this is the limit as n approaches infinity of the sum from 1 to n of f of a plus I times delta x, which is, let me use bracket there, times another delta x, which is b minus a over n. Okay, again, it's a little bit cumbersome. There's a lot of letters in there, but if you can identify all of the pieces and just keep in mind you're doing the area of a rectangle, base times height, length times width, however you want to think about it, and just in terms of the function, and then we have an infinite number of those. Okay, so let's look at an example using this limit process, okay? Which is going to turn into a definition here for us in a second. But using this limit process, we're going to find the exact area under this parabola on the interval from 1 to 3. So this is my A, this is my B, okay? So I'm going to fill in delta x and x sub I first. So delta x is b minus a, so 3 minus 1 over n, so 2 over n. And then x sub I is a plus I times delta x, which is 2 over n. Okay, let me write that. Let me put the I at the back. So 2I over n. Okay, going into this formula then. The area is equal to the limit as n approaches infinity of f of x sub I, so 1 plus 2I over n times delta x, which is 2 over n. Okay? Let's evaluate this piece right here, because we know what f of x is, so we should be able to evaluate this. So that's keeping the limit notation the same all the way through. F of 1 plus 2I over n is the quantity 1 plus 2I over n squared plus 1. Oh, I forgot my summation. Back up. The sum from I equals 1 to n. Okay. Sorry, we need to have that. I equals 1 to n of, so we're going to do that quantity squared, 1 plus 2I over n squared plus 1. So that's this part, times 2 over n, that's still here. Okay, and now we're going to do a whole bunch of algebra. So limit as n approaches infinity of the sum from 1 to n of, so I'm going to have 1 squared plus 1 is 2, plus 1 times 2I over n doubled would be 4I over n, plus this squared, which is 4I squared over n squared, and that whole thing is multiplied by 2 over n. Remember, I already added the 1 when I made this a 2. Okay, now I'm going to distribute that. Again, whole bunch of algebra. This is a little tedious, but you're not going to have to do it a ton. So sum from 1 to n of distributing, so I get 4 over n plus 8I over n squared plus 8I squared over n cubed. Okay, from here, we are now going to use our properties of linearity to break this apart into 3 separate summations, and then we are going to use the summation rules, the formulas for the constant, linear, and quadratic series, and then we are going to evaluate the limit last. Again, I know it's a lot of algebra, but we don't have to do it a ton. Okay, also I'm going to cheat a little bit and give myself more room because I'm writing kind of big. Okay, so hopefully you're giving yourself space. All right, so this becomes the limit as n approaches infinity, and then I'm going to break this, like I said, into 3 separate ones. So I'm going to, okay, 4 over n. Now, in the context of this summation, the variable or the index variable is an I, meaning anything that is not an I acts as a coefficient. Even though I have the limit as n approaches infinity, n is only a variable in the context of my limit, not in the context of the summation. Okay, so what that means is I can factor 4 over n to the front of the summation and just have a 1 left over, which is my constant series. Okay, and then I can factor 8 over n squared to the front, sum from 1 to n of, now I have the linear series, and then 8 over n cubed gets factored, and I have a quadratic series left. Okay, continuing with the limit in front. So now I have 4 over n times the constant series. The sum from 1 to n of 1 is n, etc. I'm sorry, 1 plus 1 plus 1, n times, which gives us n, which is nice because those are going to reduce. And then I have 8 over n squared times, now this is the linear series, which is n times n plus 1 over 2. And lastly, 8 over n cubed times the quadratic series right here, which is n times n plus 1 times 2n plus 1 all over 6. Okay. Simplifying the algebra, I've got, let me switch colors here so you can kind of follow what I'm doing. So I've got 4 over n times n is just a 4. Okay, I'm going to take off one of these n's. I'm also going to reduce the 8 and the 2 to be a 4. So now I have 4 over n times n plus 1, which is 4n over n, 4, plus 4 over n. Okay, so these two terms right here come from this. Write it out in 2 steps if you need to. Distribute and then reduce. Okay, plus over here, again, I'm going to take one of these n's out, make that a square. Take 2 from this, make that a 3, make this a 4. I'm also going to go ahead and multiply these two together to be 2n squared plus 3n plus 1. Okay, so now I'm distributing 4 over n squared to this over 3. Okay, and again, you can do it in 2 steps if it's a little bit too much algebra. So I have 4 over n squared times 2n squared over 3. The n squareds cancel out, and I get 8/3 plus 4 over n squared times 3n over 3, which is just n, so that's 4 over n. And then 4 over n squared times 1/3 becomes 4 over 3n squared. Once again, write it out, do it in 2 steps if you need to. Okay, now I'm going to evaluate the limit. Limit as n approaches infinity of 4 plus this has n in the denominator. Remember that goes to 0, plus 8/3 plus 0 plus 0. Okay, and then that becomes 8 plus 8/3. 8 is the same thing as 24/3 plus 8/3, which is 32/3, and then that is our final answer. Okay, getting to the definite integral, but I'm going to do it in the next video.